Hello everyone, my name is Haozheng Zhang. Today I am quite glad to present my paper, which is called Cerebral Palsy Prediction with Frequency Attention Informed Graph Convolutional Networks. Within this presentation, I will give a brief introduction to cerebral palsy and some related work. Next, I will talk about the main contribution of our work. Then, I will go through our method, which mainly consists of the frequency binning module and the CP prediction network. After that, the experimental datasets and results will be discussed. The last part is a summary of our work. Let's start from the introduction. Cerebral palsy is a common movement disorder which primarily affects movements, posture, and coordination. It is estimated that about 2 to 3 in 1,000 babies in the UK have some form of CP, which is similar to other developed countries. It means that the number of new cases in the UK is estimated to be around 1,800 each year, and CP is one of the most common motor disabilities found in children. Therefore, early diagnosis of CP is very important. One of the most popular and accurate clinical methods to predict CP is general movement assessment, which is also called GMA. GMA is a manual observation of mirroring movements that occur spontaneously in infants by trained assessors. However, the training of GMA is a time-consuming and resource-consuming task. Only a small but increasing number of clinicians have received GMA training in the UK and Australia. In recent few years, machine learning and deep learning-based methods have shown the improving and promising performance in predicting CP. However, many existing works will heavily rely on handcrafted features, which means they require considerable domain expertise and may not be transferable to another domain. These methods are also not interpretable by humans due to the black box model. In addition, there are limited works focusing on the frequency of the body movements. Motivated by the problem introduced on the last slide, we propose a frequency attention-informed graph convolutional network for CP prediction from consumer-grade RGB videos. In detail, we make our CP prediction model interpretable by the attention module, which shows the importance levels of frequencies of each joint movements. We also propose an easy-to-use frequency binning module to analyze the joint movement frequency and improve the prediction performance. In addition, we validate our system on 2 datasets and achieve state-of-the-art performance on both datasets. Our full system takes the infant's RGB video recordings as the input. Then we extract 2D skeleton features by employing a pose estimation method, namely open pose. These features include the 2D body joint coordinates, representing the joint movement. After that, we propose to use a frequency binning module to transform the joint movement features into the frequency domain, then filter high-frequency information to make our prediction network focus on low to mid infants' movement frequencies. We feed the frequency features to the CP classification network, which is a frequency attention-informed graph convolutional network. The attention module allows the system to tell us which joints are important for its diagnostic decision. The design of our frequency binning module is motivated by 2 observations. First, previous studies have shown that the body movement frequencies of healthy infants are different from infants who suffered from CP, and the low frequency range information of body movement is more critical for fidgety movements, where the fidgety movements are small movements of moderate speed with variable accelerations of the neck, trunk, and limbs in all directions. And the absence of fidgety movements is an essential distinguishing feature of the CP. The second observation is that the infant movement frequencies are generally low, and the high frequency range from the joint position data is mainly due to data noise. For example, the misdetected joint position and the video capture error. According to the observations, we use the fast Fourier transform to get the frequency coefficients of joint movements. Then, we design a binning strategy to retain the critical 0 to 5 Hz frequency information while filtering the high-frequency noise. From the equation below, we can see that this is a straightforward function. We just use a controllable parameter to decide the width of bin. We feed the frequency features to our proposed CP prediction network. Different from previous CNN-based CP prediction studies, we propose to use graph convolutional network because of its good performance in dealing with non-Euclidean structure data, such as human skeletal graph features. In addition, we use the attention module to show the importance level of each body joint by the attention value. It makes our prediction network more interpretable to the clinicians. More details and mathematical formula of our attention module can be found in our paper. From this page, we are talking about our experiments. We validate our system on 2 datasets. The first dataset is called the MINI-RGBD dataset. It is a synthetic dataset generated by registering and rendering the synthetic model to 12 RGBD video sequences of real-world moving infants about half-year-old. The second dataset is a real-world dataset, namely RVI-38. It includes 38 video sequences of different infants between 36 to 60 weeks. For each dataset, we conduct a leave-one-out cross-validation to evaluate our proposed system. From these tables, we can see that our system achieves state-of-the-art performance on both datasets. To evaluate whether there is any adverse effect on prediction performance caused by the frequency binning module or the attention module, we conduct an ablation study. Due to the limitation of the size of the MINI-RGBD dataset, the contribution of the attention mechanism is not reflected significantly. But from the larger RVI-38 dataset, it can be seen that there is a significant improvement by applying the attention module or frequency binning module. We also visualize the important level of each joint by showing the attention value. We observe that the attention value of right knee, right wrist, and left wrist are significantly higher than other joints on both datasets. It indicates that our system pays more attention to the movement frequencies of infants' knees and wrists. In conclusion, we propose a frequency attention-informed graph convolutional network for CP prediction from consumer-grade RGB videos. We interpret the CP prediction by showing the attention value of the joint movement frequency. We validate our system on 2 datasets and provide state-of-the-art performance in this task. Thanks for listening. That's all for my presentation. If you have any questions, please feel free to send an email to my email address.